Okay, today we are starting another lecture. We will continue on with the cation exchange, and today we will talk about the methods of measuring the cation exchange capacity. Several methods are available to determine the cation exchange capacity of a soil. All methods rely on the ability of an index cation to replace the native readily exchangeable ions. We know that the soil colloids will have many native exchangeable ions, different ones, and that will depend from or change from one soil to another. So first, we're gonna have to rely on the ability of an index, and that means index cation we choose to replace all the native exchangeable ions that are on the soil colloids, to remove them, to replace them, to exchange them. Two general categories of CEC methodologies are employed. General categories, they depend on the different methodologies. The first involves the displacement of native cations and the saturation of the exchange complex with an index cation such as sodium. We'll go through this in detail. So first, to displace all the native cations and saturation of the exchange complex. Exchange complex here, what we mean by it is all the colloids that can have exchangeable cations. That includes silicate clays and humus with an index cation. So we choose an ion to replace all these native cations, such as an example is sodium. Then the adsorbed sodium is then displaced by a second index cation, such as ammonium. Here, when we say the word saturation, that means all sites that can have exchangeable cations will be occupied by sodium. So the soil is saturated with sodium. The exchangeable sites are saturated. That means completely occupied by sodium ion. Then that adsorbed sodium is displaced again by a second index cation, such as ammonium. The moles of sodium displaced by ammonium are equivalent to the moles of exchangeable surface charge per mass of soil. If you saturate the colloids surfaces, the exchangeable site, with sodium, that means it's occupying all the negative charges that are there. And then you remove this sodium and collect it, so, and measure it. That means it's a measure of the exchangeable cation capacity or the exchangeable sites of the soil colloids. The second technique involves the displacement of native readily exchangeable cations by an index cation that is normally not native, such as ammonium. So in this particular method, the second method, we remove all the cations also, but by an index cation, that means an ion we know and we choose, okay, like ammonium. We choose a cation that is not normally found in large amount or very little of it, if any, on the exchangeable sites. So it has to be very little or almost none. It's not native to that soil. Then subsequent determination of displaced calcium, magnesium, potassium, and sodium, and aluminum and magnesium in case we have acidic soil. So you remove or displace or exchange all of them. All these words mean the same thing. All the native exchangeable cations, you displace them by one cation, say like ammonium. Then you collect all these. In the other place, we had them all in one, exchanged by one, and then we're gonna measure that. But in this case, we displace all the cations and we collect them, and then we determine each one of them individually. And usually we choose the cations that are most probable for that type of soil, for that climate. We should know about the chemistry of the soil in that region so that we decide which one. So in case of our soils, say in Jordan, temperate regions, so mostly they determine calcium, magnesium, potassium, and sodium. If you have acidic soils, you add aluminum and manganese. If the soil is acidic, for our case, we don't do this. A summation of the moles of displaced charge is then a measure of the effective cation exchange capacity. We call it EC, effective cation exchange capacity. So we determine each one individually, and then you add all of them in moles per charge, of course, moles of charge. You add them together, and that is our effective cation exchange capacity. This second method also allows for the determination of the exchangeable base cations present on the exchange complex, sum of the centimole of charge of calcium, magnesium, potassium, and sodium adsorbed. Because we are determining each one individually, if we add the basic ones, the basic cations, okay, we can have that. So the second allows for the determination of the exchangeable base cations present, which are calcium, magnesium, potassium, and sodium, which is sometimes important to know. Now we will concentrate on the first, the first procedure is the one really that's used most commonly in almost all laboratories. That's using an index ion and using another index ion to displace it. So we'll go through the details of that procedure. The ammonium acetate of pH 7 or 8.2. The ammonium acetate method employs two index ions, sodium and ammonium, in pH buffered acetate solution to determine the potential CEC of a soil. We'll go through this step by step and just concentrate, and it's easy, but keep in mind all the steps follow each other, and you have to concentrate on all the steps so that you understand the whole procedure. Measured CEC can either over or underestimate the field, the actual CEC of a soil, depending on the field pH of the soil. Okay, that's why we have, you see the title, we have pH 7 or 8.2. So we choose for our soils, for the conditions we have, which one is the appropriate one. Do we use ammonium acetate buffered at pH 7 or ammonium acetate buffered at pH 8.2? So the measured CEC can either over or underestimate the field, which is the actual, what we find in the field. When we mean by the field, the real pH of the soil, the real CEC of the soil in the field, actual CEC of the soil, depending on the field pH of the soil. So we don't want to underestimate, overestimate. This is not good. So how do we avoid that, and how, and when does that happen? If the field pH, the real pH of the soil in the field, is greater than the buffer pH, the ammonium acetate will underestimate CEC. Why is that? So if the field pH is greater than the buffer pH that we're using, the ammonium acetate will underestimate CEC. Remember that when we studied the sources of charges, we said there are permanent charges that are due to isomorphous substitution. These are not affected by the pH of the soil system at all. But we have pH-dependent charges. Those charges, their magnitude, their amount will change with the pH of the soil. So if the pH in the field is greater than the pH of the buffer, which means the buffer is less than the soil pH, the ammonium acetate will underestimate CEC. So that means the charges we will have in reality are less than the charges that are in the field. If you remember when we said if the pH goes higher, we have higher negative charges. Go back to when we talked about the sources of charges. The higher the pH, the more negative charges you have. If the pH of the buffer is lower, that means we don't have the real negative charges. We have less than what is supposed to be in the field. So that will end up into underestimating CEC, giving us a value of CEC less than the real CEC of the soil in the field. The buffer pH, of course, the opposite is true. We don't have to go with the other way because you can understand. The buffer pH is selected with knowledge of the soil pH. That's why we have to choose a pH here for the buffered system, which is very close to our conditions. So the buffered pH is selected with the knowledge of the soil pH in the field. For the CEC of acid soils, a pH 7 buffer is used, while the CEC of alkaline soils is determined at pH 8.2 in an effort to minimize calcite dissolution. So in our cases, in calcareous soils, in the temperate regions, we usually choose the 8.2 buffer to determine the CEC of the soil. Okay. The pH 8.2 sodium acetate, ammonium acetate method was developed primarily for application to alkaline soils, remember, so that we can be very close to the pH of the soil in the field. Soil is initially centrifuge washed a number of times with a pH 8.2 1 molar sodium acetate solution. So remember, we need to saturate the soil with sodium, which means all exchangeable sites have to be occupied by sodium. If you do it one time, you shake the soil with this solution, you cannot be sure that all the exchangeable cations were removed and sodium took their place. So we do this a number of times. That means you add a solution of sodium acetate to your soil sample, then you shake it for a certain period of time, then you centrifuge and decant, throw it away. You don't need for now to keep it. Okay, then you repeat the same, usually about 3 times we do it, a number of times, usually about 3 times, to make sure we saturated our soil colloids with sodium. The successive washings remove soluble salts and saturate the exchange complex with the sodium index. That's what I have just explained. The soil is then centrifuged, washed with 95% alcohol or ethanol solution to remove occluded sodium. When you have a soil wetted with sodium acetate solution, that solution is also between the soil particles, not only on the exchange sides, but we have solution that is wetting the soil. It's in the pores of the soil. We have to remove that because that's not on the exchange. That's what we call the occluded sodium, which was trapped in the soil between the particles, but it's not absorbed on the colloids. So we remove it with alcohol so that the alcohol will not remove the exchangeable sodium. The exchangeable sodium has to stay on the exchangeable sites. So we remove the excess with 95% ethanol. Soil is then repeatedly washed with a pH 7, 1 molar ammonium acetate solution to displace sodium for analysis. Remember, we said that's the 2 steps we have already talked about. The first step, we saturated the soil with sodium, so we have only sodium ions, and that amount of sodium that's absorbed represents CEC. So now we have to obtain it all, to get it all. So Soil is then repeatedly washed with pH 7, 1 molar ammonium acetate. So the ammonium will take the place and remove all the sodium. It will displace sodium. Sodium will come out. So we repeatedly, in this case, not like the first time, we collect every time. We do the shaking, then centrifugation, we collect that, then we repeat, so that to make sure that ammonium took the place of all the sodium. No more sodium is there. So that sodium is now collected in a volumetric flask solution to displace sodium for analysis. We need to analyze it. So, and usually you make it to a volume. You collect in a volumetric flask to make sure we can analyze and have a certain known volume. You make that mark to the mark of the volumetric flask, and it's better to use the same solution you're using. That's, remember, we talked about the matrix. Your matrix has to be continue to be the same, which is the ammonium acetate. The centimole charge of displaced sodium divided by the sample mass in kilogram is the CEC. This is the meaning. And remember the terms of expression, means of expression we talked about earlier. So you determine how much sodium, you change it into centimole of charge, and per kilogram of soil, that's your CEC. We'll take example. To go through all the steps, we take a real example and follow again the steps. That way, if you understand this, you should be able to calculate the CEC of any soil, no matter what the soil sample weight was or the mass that you started with, and what volume you collected in. It doesn't make any difference. That will depend on what do you expect, what kind of CEC you have. So the principle is the same. So let's go through this example. So if you understand it, you can apply it to any other. Okay, so we take 2 gram soil sample treated with a pH 8.2, 1 molar sodium acetate solution, followed by removal of entrained sodium, entrained or occluded, the same meaning, by alcohol, remember, by ethanol. We're just going through the steps that we already have talked about. Then the sodium saturated soil is then treated by subsequent washings, subsequent following those, with a pH 7, 1 molar ammonium acetate solution. The supernatant solutions from the ammonium acetate washings are collected. Of course, we have to collect it to measure the calcium, to determine the sodium. We have to determine how much sodium we have, and combine in a 50 milliliter volumetric flask. So we collected them in 50 milliliter. Of course, what you collect is impossible to come to the mark. Either it has to be lower, it should be usually lower, which is brought to volume with distilled water. Here he says distilled water. I rather go with the ammonium acetate to keep it the same, because it doesn't make any difference here, because the amount is very little. You talk about most of the time less than 1 milliliter, you have to bring it to a volume or so. So even if you did it with distilled water, it does not change the matrix very much, but it's better to keep up with the same matrix, bring it to volume, bring it to the mark with the ammonium acetate. The solution is analyzed by atomic emission spectrometry for total sodium. So that 50 ml contains all the sodium that came from the 2 grams of soil, which was on the exchangeable site, which represented the CEC. It's all in here now. So we go and determine how much sodium is that in this solution by atomic absorption, emission, whatever. We can also do it by flame photometry. It doesn't make any difference. You have to determine analytically and correctly. Okay, let's go through the real calculations. If the total sodium concentration was found to be 119.4 milligram per liter, remember, milligram per liter is also what we call parts per million. So this is the concentration of sodium in that 50 ml volume that we collected. Then 50 ml contain all the sodium is in the 50 ml. So we want to know how much sodium in the 50 ml. This is concentration. It's given by milligram per liter. We don't have a liter. So you say 119.4 milligram per 1000 milliliter, which is the liter, times 50. Okay, so you want to know how much this amount is found in a liter in 1000 ml, but I have only 50 milliliter. So you multiply by 50, you get 5.970 milligram of sodium. Okay, now we know that the atomic weight of sodium is 23. So 5.970 milligram divided by 23 milligram times, to get it in millimole. Remember, milligram gives you millimole, gram gives you mole. Okay, so this is easier instead of changing it to grams and then mole and then back again. No, remember, because they all divided by 1,000. Milligram, millimole, gram, mole. So we divided by 23, which is like milligram per millimole. So they will times the millimole equals 0.260 millimole. So we have in that 50 ml now, the total sodium we have is 0.260 millimole of sodium. 0.260 millimole over 10 millimole per centimole. Remember, the units we need are centimole. Remember the units we need, centimole of charge per kilogram of soil. So we want to change the millimoles, you divide them by 10 to get them into centimole. So now we have, instead of 0.260 millimole, we have 0.0260 centimole of charge. We said charge immediately because sodium is monovalent. So it's the same, the centimole or millimole of sodium, because it's monovalent, carries one charge, it will automatically be also centimole of charge. If it was divalent thing, we have to do different thing. Remember, we have to divide and multiply. Whatever you learned how to do things, you have to change it to centimole of charge. But here we're dealing with sodium monovalent. Same millimoles, centimoles of sodium will be giving us the same of the centimole of millimole of charge. So the CEC, now remember, we want centimole per kilogram of soil. So this amount that we calculated was in 50 ml. And it came from 2 grams of soil, remember. So 0.0260 centimole of charge per 2 grams of soil. That's what we started with. That's where all the sodium came from, 2 grams of soil, times 1,000 gram. We want in a kilogram. So 1,000 gram per kilogram, we have 1,000 gram for each kilogram, equals 13.00 centimole of charge per kilogram. So that is how you can calculate CEC regardless of the type of samples you had, ion we have. It doesn't make any difference. The procedure is the same. Concentrate on the method, on the principles, then you will never make a mistake in calculations. Okay, this is something, it's in your book in the last end of the chapter, and I'll go through it quick because one of your presentation, big presentations later, will be based on that, will depend on that. So how do we identify minerals by X-ray diffraction analysis? First of all, we should know that the X-ray diffraction analysis is semi-quantitative identification. Semi-quantitative, it does not give you how much you have of any of the silicate clay minerals in the soil, but the amount of peak, as we will talk about the peaks later, and you will talk about them also in your presentations. The size of the peak gives you an idea about, do you have a very trace small amount or large amount, but that's we call semi-quantitative, but not an amount. It doesn't give you have 10%, you have 15%. You cannot do that. For quantitative analysis, we need the following. If you want to do really quantitative analysis, you need to do the following: chemical, thermal, infrared, surface areas, all of these together, and then from those you can determine the amount of silicate clays or any of the silicate clays you have in the soil. Now, for the identification of minerals by X-ray diffraction, we use, or what's used according to the law, which is called Bragg's law. Remember, the apostrophe has the name of the scientist is Bragg. Bragg's law, the law of Bragg. N lambda equals 2D sine theta. We will see in a diagram what do we mean by all these. So n is an integer. Integer, that means it's 1, 2, 3, 4, whatever. It's a whole number, no fractions. Lambda is the wavelength of the X-ray radiation that we're using. D is what we call the distance between planes of crystals. We'll look at the diagram in a second, and we'll see that D. Theta, the angle at which the radiation strikes the crystal surface. Okay, this is a drawing or diagram that will show you how the Bragg's law works. Identification of it by Bragg's law. Okay, so if you see, this is X-ray ray 1, and this is another X-ray ray 2, sorry. They both, this first X-ray hit the surface of the crystals. The crystal, remember, we have clay particles. You grind them fine, or there are different ways of doing it. And that, again, you will cover it in your presentation. But some of that X-ray will be reflected right away from the surface. So A to A prime, this is the theta between the surface of the clay that was hit by X-ray. That angle is theta. And of course, we can control that by the machine. We have the X-ray machine that we expose the samples to. We have full control of this theta. Okay, so it's reflected. And remember, the angle of the falling ray should be equal to the angle of the reflected one. You learn that in physics. So this theta and this is also theta are equal. The second ray penetrated the clay and sorry, it was reflected from the second surface. So this B prime, okay, this is what we call the D spacing, this distance. Now this is the top of the first crystal unit. Remember the crystal unit or layer we already talked about. If you don't remember it, go back again to the fundamental structure of clay minerals, how we talked about them. So this is the top of the first crystal unit. And this is the top of the next crystal unit, not the bottom of the first crystal unit. This is the top of the next crystal unit that's adjacent to it in a crystal, in a particle. So why is that? So that this D will include any space between them. Remember, we have the 1-to-1, there is no space between them. We have the 2-to-1 expanding variable, that space is expanding. So it depends on what type of clay and what condition it is. So that D will be variable and will change by the expansion of the clay. It's included in that D. But if you have non-expanding other mineral, say the non-expanding 2-to-1 minerals, this D is basically also fixed for that type of mineral. It doesn't change very much sometimes. So now you can see all the parameters here. So the experimentally measured parameter D over N, usually for you to just make it simple, take N as 1. So D will be the D that we're interested in, this one between the first and second crystal units. equals lambda over 2 sine theta, is what we call the D spacing. That D is called D spacing because it's very characteristics of each clay mineral. Clays will give characteristic D spacing. That means it's only special for them. That's what we mean by characteristic D spacing. It's for each type of crystal, for each type of clay minerals, it is special for it. It does not, you don't apply the D spacing for the same number for all clay minerals. No, each clay mineral has its own D spacing, and that's what we use to differentiate them based on that. And read, there is a paragraph in your textbook where they talk about that, and see how does that D change, what makes it change, how we can use it, and again, utilize that information to make sure what kind of silicate clays we have in the soil. So we can use it at different temperatures that are diagnostic for their identification. Again, I will not go through this because you will have your presentation, big presentation on that, but this will be a good introduction for you to learn a little bit about it. And it is good for you to learn how to derive this. I want each one of you, because in your exam, hopefully we will have exams, inshallah, when things go back to normal. I want you to know how to derive this. The derivation is on the internet, but I want you to know the exact details of how, from the triangles you see, from the angles you see, how did we derive that D equals lambda over 2 sine theta. Theta is here and D is here. So you have D, you have theta, that's all you need. How to derive and prove that this, from this figure, the Bragg's law, that it is this way. This is gonna be a little bit long lecture because I want to finish this part completely, so the next time we start a new thing, we will remember we just said that to determine quantitatively the clay minerals, we have to go through chemical analysis, through many different other analyses. So if we did analysis, how do we calculate the structural formulas and CEC of clay minerals? We'll go through the steps. This is again, and this is in your book. In a minute, I will tell you the table we will be concentrating on, and you should have that table next to you when you study these lectures or these slides, the coming slides. Such information can only be ascertained through chemical analysis. So only through chemical analysis. We cannot do it by X-ray, not by infrared, but only you have to do very thorough chemical analysis. In calculating the structural formulas, it must be assumed that the SiO2, Al2O3, etc., that are reported were a part of the clay mineral structure. So when we determine, we will see in that table that I will refer to it in a minute, they will put the amounts of oxides. This has been a very old way used by geologists, and many other scientists do the same thing. It doesn't mean you have SiO2, Al2O3, no. You express it in terms of oxide. Just like if you remember in fertilizer, we say potassium as K2O, and phosphorus in the fertilizers is expressed as P2O5. These do not exist in fertilizers. They are means of calculating. This is the same way when we say oxides, we do not mean we have SiO2, Al2O3 in the clay minerals. No, the silicon was put in terms of oxide. The aluminum was put in terms of oxide, and so on. So we put all the elements we determine in terms of oxide by calculation. It has nothing to do with the structure that you are talking about. So that are reported were a part of the clay minerals. So these has to be, that means if I say SiO2 in that table we will see, that means silicon is only coming from that structure that we are talking about. It's not coming from quartz, from other primary minerals, from other. No, you have to concentrate only and separate that clay minerals, so all your concentrations that you have belong to that structure that you're dealing with. Example, so we'll take an example which is same as in your book. I'll go through the example they gave so they will understand it when you study. A 2:1 clay with an ideal formula of Si8, Al4, O20, OH4. Remember, tetrahedral, octahedral. Remember, this is in 2 tetrahedral, remember, 2 tetrahedral sheets, 1 octahedral sheet in the 2:1. So the aluminum will be in the octahedral sheet. Silicon will be in the tetrahedral sheets. And of course, the OHs in the octahedral and the oxygens in the tetrahedral. Thus, there are a total of 44 positive charges, 44 negative charges. If you multiply Si4 times 8, 32, plus 4 times 3, that's 12, okay? And that will give you the 44. Okay, here you have OH negative, 4 negatives, and 20 by 2. This is 40, 40 and 4, 44 negative. So you have 44 negative, 44 positive charges in this structure. It is inert, it's neutral, no charges. So this is the ideal form. To calculate the structural formula for this clay, the following assumptions are made. A total of 8 atoms can fit in the tetrahedral sheet, which can contain silicon and aluminum. Remember, we said silicon is the normal ion that we find in the tetrahedral, but it can be replaced in isomorphous substitution by aluminum. So if you don't have all the 8 positions occupied by silicon, the rest of them will be occupied by aluminum, the only choices. A total of 4 atoms can fit in the octahedral sheet with aluminum. Here we have many choices: aluminum, iron, ferrite, ferrous, magnesium, and lithium. They are all able to fit in this sheet. So this 4 can be aluminum and some of those too. Larger cations such as potassium, sodium, calcium occur as exchangeable cations. Remember, those colloids always have negative charges, and the negative charges have exchangeable cations. We just talked about CEC. So the exchangeable cations are there to neutralize the negative charges. These, we cannot calculate them as part of the structure. These are external. So these large ones, if we determine potassium, sodium, calcium, they do not go into this structure. They are exchangeable cations on the colloid. So keep this table 2.9 in your textbook, page 70, next to you when you study this, okay? So table 2.9, page 70, all the information that I will talk about and this example is coming from that table. So we're taking example SiO2, the weight percent, the one that's giving in the table how much SiO2, 50.95, which the molecular weight of this, sorry, if you calculate the molecular weight of this, 60.06. The amount as percentage in that sample we have, the 2:1 clay minerals we are studying, 50.95. So to make things easier for you, assume we're having 100 grams, 100 grams. So 50.95 grams out of those 100 grams will be SiO2. So the 50.95, we divide it by 60.06 to get the moles, or we call it formula weight of SiO2, or in other words, the moles. Remember, mass per molecular weight or mole. So we get 0.848 moles of SiO2. Okay, we're interested in charges, remember. So each of those has only one silicon. The SiO2 contains only one silicon, and that silicon has 4 positive charges. So 0.848 times 1 silicon times 4, which is the charge, equals 3.39 gram equivalents of silicon. So gram equivalent, which is really indication of the charges coming from silicon. Total gram equivalent, remember the equivalent, when we talked about the centimole of charge per kilogram, they used to say milli equivalent per 100 grams. So the equivalent is an indication also of charges too. So we have total gram equivalents of cations in all. If you look in your table, add them all will be 4.754. Total of the gram equivalents, if you add them for that particular example, 4.754. All the equivalents, all the moles of charge. The gram equivalent of silicon in total full cell. So what is the contribution of silicon from this total? We calculated with 3.39 for silicon, divided by 4.754. And remember, we said we have 44 positive charges. Remember, 44, we said we have 44 positive charges, 44 negative charges. Okay, the contribution of silicon 3.39 out of the total 4.754. This is a fraction of what? Of the 44 charges. So when you multiply it, that means we have 31.376 charges coming from silicon. Okay, we now know that each silicon, we said already, has 4 charges. So if I want to know how many silicons contributed this number of charges, atoms of silicon per unit cell, we divide this number of charges per 4, so I'll give you 7.844. So that means I have the number of atoms of silicon in that structure is 7.844. You might question, how can we have fraction silicon atoms? Of course, you can't divide an atom. You can't cut atoms in pieces. But what it means when you have a structure with thousands and thousands and thousands of silicons in it, so that fraction means, like if you have, say, 10,000, you will have out of those 10,000, 7,844 silicon atoms. So that's what it means. So in that total, you will have, if you have, say, that's how you should think about it, not a fraction of an atom, but this is a percent. Just like when we say, okay, the population growth is 3% or 2.5%. Do we divide the human being in 2.5? No, but you take 1 million, you take 10 million, you take whatever number of population you, and that number will, you multiply it by a certain number, then it becomes whole number, become real thing you talk about. This is the same thing. Think about it the same way. So there are 7.844 silicon atoms present in the clay mineral. Remember, we have in the ideal thing 8 positions, 8 atoms, but not all of them now we know occupied by silicon. Only 7.844 are occupied by silicon out of these 8. A total of 8 atoms can fit in the tetrahedral layer. We know that already. Therefore, the remaining 0.156, if you subtract 7.844 from 8, you get 0.156 atoms in the tetrahedral. And we said the only atom that can replace silicon in the tetrahedral is aluminum. So that rest of it will be aluminum. So now we already know in the tetrahedral, this sheet has the cationic composition Si4 for charges, the charges of it, 7.844, and the aluminum 0.156. So this is in the tetrahedral sheet. So already we know the structure on the tetrahedral sheet. How does it look? The remaining aluminum atoms, remember, you will see in the table, the aluminum atoms calculated the same way. You can go through the calculation just like we did with the silicon. 3.005, this is from the table. Subtract 0.156 that we already said, already replaced silicon in the tetrahedral. So they are occupying the tetrahedral places here. So what we have remained, 2.849 will go into the octahedral sheet. These will go into the octahedral sheet. Then enough ferrous magnesium will be used to yield the 4 atoms. Remember, we had 4 positions in the octahedral sheet. So we have that many of them aluminum. The rest has to come from the others, either ferrous, magnesium, fraction of those. We will see according to what did we find from the analysis, the chemical analysis of the structure. The overall positive and negative charges are calculated. The net charge on the unit cell is calculated. We'll continue to finish it up. The octahedral layer would have the composition Al 2.849. Remember what we get from subtracting the amount that was in the tetrahedral from the amount that's there from the analysis, and you go do the calculation Fe3 plus the ferric, calculate, you will find it as 0.170, just like we did with the silicon. Same way, use it for all of them. Ferrous 0.033, magnesium 0.2948. Note that 2.849 plus 0.170 plus 0.033 plus 0.948 equals 4.00. From analysis, magnesium atoms per unit cell is 1.069. If you calculate the number of atoms of magnesium, they are more than what we used here. This is the only place it will fit. So all the amount we put here. This one, the full amount we put here. Magnesium, we can have it either here or exchangeable, because it also can be exchangeable. So we see the total is this, 1.069. We did not use all of it. We did not need all of it in the octahedral sheet. We needed only 0.948. So from analysis then, magnesium atoms per unit cell, 1.069 calculation. The remaining subtract 1.069, which is found by analysis, minus what we needed for the octahedral sheet. The remains 0.121 atoms would be as exchangeable ions. So the net charge on the unit cell is minus 1.14. If you calculate the negative and positive, okay, calculate them, use that. You know how to use, multiply all the positive with the negative. This one has 3 positive charges each. This one has 3 positive charges each. This one, 2. This one, 2. Multiply them all. Find out how many charges we have in the positive, and the silicon also in the tetrahedral. And then the negative charge is constant. You do not exchange oxygen or hydroxide. It's fixed. So from the difference in the two, you find the net charge on the unit cell is minus 1.14. Okay, we finished our lecture. We finished